So what I'm going to talk about today is part of a work in progress. So I would really love to have your feedback. I'm working on a book now, and I think about the book is about what sort of social science in the digital age. So I see sort of two very distinct communities. I see social scientists doing cool stuff, but they could really benefit from seeing what data scientists are doing. And I see data scientists doing cool stuff, but they could really benefit from seeing what social scientists are doing. So this book is about sort of trying to bring together the ideas of these two communities. So I see that also one challenge with doing a project like this is that you're speaking to a mixed audience. And I see here there's also some mixed audience. So there's some social scientists here and some computer scientists here. So if I seem to be belaboring some point that you think is totally obvious, that's because my guess is it's not obvious to the other community. And if there's stuff that you think is really interesting or important that you think I'm leaving out, definitely feel free to jump in. OK, so one of the questions that I think must be addressed before you work on a book project such as this is one that a lot of my colleagues ask me. In secret, they're like, hey, Matt, by the way, like, isn't this big data stuff just a fad? And the answer is definitely no. So I think the word big data is absolutely a fad, and it looks very fad-like. But what this actually represents, it's not a fad. It's a fundamental change in the world. So in sociology in particular, and in general academic fields, certain things become popular, and then like in sociology for a while, there was like a Marxist turn, and then everyone started having a Marxist kind of approach, and then people started becoming neo-Weberian, and then like there are these sort of academic fads, but those are fads because they're driven by sort of discussions happening within the field. And what I see is really different about big data, for lack of a better word, is has nothing to do with what sociologists or social scientists are talking about. It has to do with a fundamental change in the world. And that fundamental change, the change from the analog to the digital, is something that is happening, has happened, and is not going to go away. And progress will continue very quickly in this dimension. And so our choice is really to take advantage of that progress or be left behind. But I do think there are kind of this concern about fads, I think, is beautifully captured by this model, which some of you may have seen. It's called the hype cycle. So it's used to understand when a new technology enters the system, how people think about it. So here, the x-axis here is the time, and the y-axis is the visibility. So initially, things come in, and then all of a sudden, everyone thinks, oh my god, this is going to be the greatest thing ever. And then people are like, oh no, this is totally terrible. And then eventually, like, the technology becomes normalized part of everyday life. And so I think for different people are in different parts of this curve in the big data space now. So I think maybe in this room, maybe more people are here, or maybe they're, I don't know where everyone is here. But one of the goals of my book is to really sort of damp this down a lot. So pull down that peak, push up that trough, and then get to the part where this is just a normal way of doing social science. So now most of the setup really why I think what I'm going to talk about is important. I want to contrast it with most of what I see as computational social science now. So this is a picture of footprints on the beach. And I think most of the data that people are analyzing now about social behavior is this kind of footprints or digital exhaust. So this is data that's generated as a byproduct of everyday life. And researchers have expended a lot of energy trying to get this data from companies or scraping it from the web and then doing lots of analysis with it. So most of the computational social science work is this kind of work. And the metaphor that people use about this is they say, oh, this is like the microscope, or this is like the telescope. And I think that's totally the wrong metaphor. So even though this data is shiny and new, the better metaphor is that this data is relics. This is like archaeology. Basically, we have a bunch of junk. Not junk. I mean, sure, this is a very nice pot. We have a bunch of stuff that has basically been left behind. And so were you to go to an archaeological dig and work with pottery shards, a lot of questions would come up, like, why did some things get saved and not other things? What can we infer from the shape of this pot about these people's attitudes or opinions? So like, in a lot of ways, these pottery shards are not the strongest form of evidence that we can have about how a society works. Like, what we would really like to be able to do is go and collect the data that we want, not just be stuck with the data that we have. And so this is sort of the main argument of the book. So there's going to be 7 chapters. The main chapters are these 4 here about different ways that researchers and participants can interact, how the data is collected. That, I think, is the main way to think about all these different things that are happening, rather than thinking about, oh, this is like Twitter data, and this is Facebook data, and this is Google data. That is a very time-specific way of thinking, and I think that there are sort of more general and kind of timeless ways of thinking, so that when some new platform emerges, we don't want to go through the same, like, we've spent a lot of time, we as a community have spent a lot of time trying to learn from Twitter data, and we've stepped in some potholes during that process, and like, we don't want to have to do that every time some new platform emerges. And we know that new platforms will emerge, new sources of data will emerge. That is something we can predict with high confidence. And so if we want to learn from those things quickly without repeating all those same mistakes, we need to abstract away and have some more general principles. And so in my mind, the way of thinking about these is thinking about how the data is collected. So most of the data is this observed data where we basically just watch people and see what they do. And then the book is really an argument that you want to move down this list. You want to have more and more interaction with the participant, more and more control over the data you're collecting. So then you can sort of ask people questions. This is like surveys. You can do experiments, or you can do mass collaboration. So as you go down this list, it gets harder and harder to do, I think, but the benefits can be greater. And so in my own work, so what I'm going to talk about today is collaborating. So in my own work, I've done some previous stuff on new forms of surveys. This is, Michael mentioned the wiki surveys. And I've done some stuff on new forms of experiments. This is like the music experiment, online music experiment. And I have not done as much about new forms of collaborating. But to me, this is the most exciting, because this is, to me, offers the greatest possible improvements over what we're doing now. But it also seems the hardest. So I'm really stumped about how one would go about doing this, which is part of the reason I'm excited to be here. So now I'm going to sort of walk through how I think about this space, what I think are the problems, and in general, I'll sort of offer a topology that I think is useful for social science, and then I'll give an example in that space that you might be familiar with, and then I'll give some examples from social science that you might not be familiar with. And also the idea is that in social science now, the bar, there's so much skepticism about this. Like if I seem to be overly defensive and overly pessimistic, that's because when I talk to social scientists about doing these kinds of mass collaborations, they're very, very, very skeptical. So the kinds of claims that I'm going to try to make here, I think are very, very modest. And that sort of explains the tone. The tone is sort of where I'm coming from. OK, so for me, a really inspirational example is Wikipedia. I just love Wikipedia. It is so cool. This group of distributed volunteers around the world has produced this amazing intellectual product. And it wasn't new knowledge that was really necessary for Wikipedia to form. It was a new form of collaboration. So Wikipedia allowed people to share and aggregate the knowledge they had in a new way, and it produced this beautiful thing. And so one of the things I see a lot of these digital age tools enabling is new forms of collaboration. So now that we already collaborate on our research, right? We work with our peers, we work with advisors, we work with colleagues. There is already collaboration in research, but now we can collaborate in much different ways at much different scales. So can we use the tools of the digital age to enable new forms of mass collaboration to solve scientific problems? So here's how I think about chopping up this space. So I think that you can use mass collaboration for data analysis or for data collection. And then within data analysis, I think you can either specify a clear task, and this leads to human computation style work. You can specify a goal, and this leads to more open call style work. And you can also just have straight up data collection. And so from my perspective as an outsider in this space, I see lots of work happening in this part of the space. Like, how can we do more MTurk style stuff? And I think there's a lot of opportunities here to do different kinds of things. And I was actually really excited to hear that lots of the people here in the HCI group are working on moving into these other parts of this space. Because I think these are the parts of the space that are potentially more interesting to me as a social scientist. Like, these are the things that I would really like to be able to do. And I don't really know how to do them. So let me now, so I'm going to sort of walk through each of these categories. And I should, again, say, if you have any questions or comments, feel free to jump in. Yeah?
So I might have something in the beginning. Sure. You're thinking of problem solving rather than just data collection. That also should be in your space of collaboration, right?
Yeah, so I would say that problem solving, I would sort of put in with data analysis and data collection. And so one other thing about this topology, someone asked me like, oh, like, where did this come from? Like, what principles lead you to this topology? And there are no principles that lead to this. This is just like my reading of this and thinking about it in a way that I hope will be useful to social scientists. So I should also say that part of the reason I think I ended up in this space this way is that these sort of map on to ways that social scientists already think about collaboration. So human computation is a little bit like hiring a bunch of research assistants. Open call is a little bit like talking to skilled experts or soliciting ideas from skilled experts. And distributed data collection is something that we already do when we like hire a survey firm. So we would pay people to go out and interview other people and give us the data. What if we could sort of do that without paying people through a firm? So I think these sort of implicitly map onto things that social scientists are doing already. OK. So human computation. So I think one of my favorite examples of this is Galaxy Zoo. Just as a show of hands, how many people have like seen Galaxy Zoo? OK, good. OK, about half. So basically, astronomers are interested in galaxies. And I'm going to totally butcher everything about galaxies because I'm not an astronomer. But as a crude approximation, for the purposes of this talk, there's two main kinds of galaxies. There are elliptical galaxies and there are spiral galaxies. And galaxies also have different colors, red and blue. And so roughly, they wanted to know something about the prevalence of red elliptical galaxies and red spiral, like the relationship between color and shape. And so it turned out to, so that's the problem. And they have a picture of a bunch of galaxies that were taken by telescopes. So at the time, it was very hard to train a machine. This is around 2007. It was hard to train a machine learning classifier to distinguish between spirals and ellipticals. So you needed to do this by hand. So a graduate student named Kevin Shawensky worked for 7 12-hour days and classified 50,000 galaxies. This is a lot of work. They wrote this nice paper about it. But the problem is that this was only 5% of the galaxies that they had photographed. And it also turns out that now newer satellites capture on the order of 10 billion of these images. So this approach is not going to work. Need to scale it up more. So Kevin and Chris Lintott and some other people created this website, Galaxy Zoo, where anyone in the world could come and classify galaxies. And so the volunteers had a very short training, so only a couple of minutes. And then they had to pass a simple quiz. And then they were astronomers. That's it. They didn't need to go get a PhD from Stanford, just this 5-minute training. They could classify as many or as few galaxies as they wanted. And then much of the recruitment happened through the media. It didn't happen through Turk or anything like that. This was volunteers who were coming to participate in a scientific project to help further the goals of astronomy. So what happened? So over the course of a couple of months, they had 4 times 10 to the 7th, 40 million classifications. And the distribution of classifications per participant is something that you would probably be very accustomed to seeing, which is not something that social scientists are used to seeing. But you have a small number of people who are contributing a very large number of classifications, and a lot of people who are contributing a few classifications. So there's very unequal amounts of information contributed per person. So then you have all these 40 million classifications from a bunch of people. How do you put them together and get one consensus classification? So there's sort of 3 main steps, and this will be familiar to people who have done these kind of human computing projects. So first you clean the data so they get rid of things that appear to be people trying to manipulate the system, like people who have classified the same galaxy many, many times. Then they debias. This debiasing step is really important. So if you average together a bunch of contributions, that only can remove random noise, and it doesn't deal with systematic biases. So for example, it turns out that far away spiral galaxies look like elliptical galaxies. And so there's this bias built in to the way that people do these classifications. And these astronomers were very sensitive to these biases, and they built studies into the original Galaxy Zoo to measure these biases. So then they did this debiasing step, and then they did a combining step where they sort of essentially did a weighted average, where you've seen probably things like this before. They tried to give more weight to the people who seem to be better classifiers. So you put all this together, and the quality of the classifications that come from this crowd process are comparable to those that come from the astronomers, but they're 10 times bigger. And this enables them to do new science. This is the extra part that I think is really important. This enables them to do new science. So it enabled them to understand this relationship between galaxies, and it's led to a number of other sort of scientific advances. So I like this, that here this human computation goes directly into the service of some scientific problem. And so the general recipe is you take this big problem, you split it up into lots of little problems, then you apply some human work on each one independently, and then you combine them all together with this debiasing and cleaning and some kind of weighted averaging. So how could you use this same split, apply, and combine recipe for a social science kind of problem? So I'll give you an example now. So first some background. So political parties, they publish manifestos during elections. So these are documents that sort of lay out what are the goals of the party during that particular election. And there's something called the Manifesto Project, which is a collaboration of political scientists, mostly in Europe. And they have hand-coded 4,000 of these manifestos from nearly 50 countries. So here's an example of what a piece of one of these looks like. So this is from the Labour Party manifesto from the UK from 2010. Millions of people are working in our public services, embody the best values of Britain, helping to empower people, and so on and so on and so on. So that's the kind of text that they're working with. And then they have these experts code this to assess the political positions that are being taken by the parties. So imagine if you were a political scientist and you wanted to understand, like, what's the dynamics of competition between political parties, and how does that differ across countries in Europe? That's the kind of question that you might ask. And these manifestos are very valuable data to answer that question, but it's very difficult to extract the kinds of signal that you want from this kind of text. And so the way they had done it in the past is with these experts doing the coding. So in this way, this is like the picture of the galaxy in some sense that needs some human work done to it. So then this more recent paper by Benoit and colleagues, they say, let's try to turn this into a human computation system rather than giving it to the experts. We'll give it to a bunch of volunteers. So they do this, and they code up the economic positions of these platforms and the social positions, and the expert coding and the crowd coding match. So what I love about this paper, though, is that this is not the end of the paper. This is the beginning of the paper. So first they show, OK, we can turn this over to the crowd. And then they say, but what extra does this give us? And so they argue that this new process is not just cheaper or faster. They argue that it's actually better. And so this is the thing that I see. I wish more human computation work could sort of express this more clearly about how it's better, not just cheaper or faster. I like cheaper and faster. I'm all for that. But like, I think better is also cool too. And so like, one of the ways that they argue their human computation thing is better is they say it's more reproducible. And so by that, what they mean is ideally, you would take the rawest form of data you have and all the way to your final scientific conclusion and be able to reproduce that entire pipeline. Right? That is a goal. And if you're using expert codings from the Manifesto Project, you can't do that because the rawest data is the text and you don't have that anymore. You can't access that directly. All you start with is the expert coding. And how do we know how good this expert coding is? There's actually a lot of debate about that and how could that be improved. It's kind of a mess. So with this sort of crowd-based approach, they actually do an analysis and then 2 months later they do the exact same thing and they get the same result. And to me, that's a very powerful kind of argument for why. And it's actually super easy. Like all the stuff that you can do in a human computation system, it's not that hard to just do it again a month later and show you get the same thing. And it's a nice added check about the quality of your system. So they say not only is this cheaper than doing it with experts, it's actually more reproducible and then it gets us from the raw data to the final output. And it's also more flexible. So they demonstrate one issue that is becoming increasingly of interest to political scientists is policies about immigration. And when this coding scheme was developed by the experts, it was in the mid-'80s, and immigration was not a major issue in Europe. And so none of these manifestos had been coded for positions about immigration. And so they said, well, it would be virtually impossible for us to go back to all these experts and recode all these things about immigration. But our system is like really flexible, and so we can customize it to the kinds of data that we want to collect. And then they collected the data about immigration that they cared about. And so I guess another way of saying this is another way that you can sort of say it's cheaper and faster. That also means it's more easily tailored to the kinds of problems that you care about. And so that can lead to better data and better science. So this paper is in press, and I really like it. OK, so I guess the kind of claims, yeah?
What do you think motivates people to participate in these mass collaborations?
That's a good question. So I did not say this one uses CrowdFlower. So this one is money. Galaxy Zoo is love of science, excitement. I'll talk a little bit more about motivation at the end, but I do think that's like the biggest problem. Like it's pairing people who want to do stuff or to some scientifically meaningful task, and that's, I think, still more of an art. I don't know. I mean, that's why. I don't know. I mean, so like what I would say is people do it. And like we can try to figure out why they do it exactly and why they don't do it. But I find that those things are very hard for people to, like, how would you figure out why people do Wikipedia? You could ask them, but is that even really going to be helpful? So that's part of the reason that I like a lot of this talk is just examples, because I feel like in this kind of setting where it's not really clear what's going on, like an example-based approach is really helpful. I mean, people do Wikipedia. Why do they do it? I don't know. Yeah?
You were saying that a very few number of people contribute the most.
Yes.
What is the quality of their contribution compared to the majority of the people?
Yes, that's actually a very good question. And so it turns out to be the case in some of these projects, but not all of them, that the people who contribute the most are the highest quality workers. So the fact that most of the data is contributed by a small number of people is actually a good thing, because those are the highest quality workers. But this issue of worker quality, I'm glad you brought that up. So I think a lot of social scientists are used to, I don't know if you're a social scientist or not. Yeah, so I thought I could tell by your question. So a lot of social scientists who have hired research assistants before, they're like, man, it's hard to work with research assistants. Like Stanford undergraduates, very smart, very hardworking, heavily screened population. Like these should be and if you try to hire them as research assistants, it's going to be hard, and you're going to have to do a lot of quality control. And it seems like, how could you, if Stanford undergraduates are so hard to work with, how could you possibly like just have anyone in the world do it. But I think the difference is that quality control in a lot of these projects comes through redundancy, not through skill. So there were 40 classifications per galaxy. And like, if you had that level of redundancy, with your research assistants, you wouldn't need to be as careful about what each one of them is doing. So right, you need to be super careful because there is no redundancy. And so I think like one way to think about it is like quality through redundancy. Yeah? Yeah.
It's not clear that it's an entirely deterministic process. There were a number of collectively editable encyclopedias at the same time that Wikipedia was created, all of which failed. So the motivations are still there. Like, seeing something wrong on the internet is a very strong motivator to fix it, for example. But it's not enough. Yep. So there's a certain amount of
What made those fail in Wikipedia?
talk to Benjamin Mako Hill. He'll have all the paper to show you.
Yeah.
But I think we don't know. I mean, I think there's, just as I indicated in the intro, like the Music Lab experiment, there is some amount of it that is makes it feasible that it might succeed, and beyond that, if it does succeed, you can say something about the processes that would have generated that, but if it doesn't succeed, you can't guarantee that it wouldn't have happened the other way around. Like, look also at Reddit. There's Eric Gilbert has a great paper where he shows that basically stuff gets reposted all the time, and it's almost random which one of them ends up making the front page. Like, it's just path dependence. Who were the first few people, and do they get into it, and does it build a community?
Yeah. So I want to say one more thing about participation, because I think this is something that also a lot of people think about. So a lot of people start with themselves and then try to build out. They're like, oh, would I go online and classify these galaxies? No, I wouldn't do that. I'm really busy. Like, I don't have time to do that. And then they're like, well, would my friends do that? No, I don't think they would either. So no one's going to do that. So they start with themselves and build out. But that's the wrong way to think about it. I think the right way to think about it is think of the entire set of people connected to the internet. And then if 1 in a billion of these people do it, your project will be a failure. If 1 in a million of these people do it, it could be a success. And like, we have to acknowledge that it's very hard for us to anticipate the difference between a 1 in a million and a 1 in a billion. And so it's really hard to know ahead of time whether it's going to work or not. That if you're not using one of these micro-task platforms. I think that's one of the problems is, and it also takes a while before you fail. So you might invest a lot of time building one of these things, and then no one shows up, and you failed. That's really bad. So I don't really know how to make it easier to fail faster or somehow make it easier to anticipate whether it will be successful. Okay. Okay, so there's some very simple claims here that I want to make. Human computation can be used for real research, like Galaxy Zoo. That was about really advancing astronomy. They made real advances in astronomy from that data. And then also human computation can produce better data, not just cheaper data. Okay? So now I want to move on to open contests. And so I want to talk briefly about the Netflix Prize and some specific aspects of the Netflix Prize that I think make it really, really cool. So Netflix recommends movies to you. These, by the way, are not my recommend. This is something I took off the internet. Like I mean, I might like. I've never seen 300, but I might like it. So basically, what Netflix does is they take the ratings that you've given to movies, and then they try to guess what ratings you will give to other movies based on the rating patterns of yourself and others. And so they want to. It's really important to them to be able to predict what movies you'll like. And they launched the system around 2000, and then they refined it over the course of about 6 years, and it got better and better and better. And eventually, they kind of got stuck. It wasn't getting any better, and they had worked really hard on it, but they knew there were some better ideas out there, but they didn't know quite where those ideas were, and so they decided to have an open call. So basically, what they did is they released 100 million movie ratings, held back 1.5 million movie ratings, and had a contest for anyone who could come and predict these held back ratings. So roughly, this is what the data looked like. You had a bunch of users, you had a bunch of movies, you had some of the ratings were given, and some of the ratings you had to predict. So here, this is different than these human computation problems because here, the goal of what you're trying to do is specified but not the task. They don't say run a regression to predict this. They say predict these movie ratings and do it however you want. Okay. So they offered a prize of $1 million, and they opened this up to everyone in the world. And then they received close to 45,000 submissions. Now this seems like a horrendous situation. So imagine you getting 45,000 emails full of code and crazy whatever. And like, that is not what they had to deal with though. So what they were very lucky or very smart, or the way this was set up was very nice, which is that it's very easy for them to check these submissions. All they have to do is just calculate the root mean squared error. It's super simple. So something about the way this problem is set up enables them to be open to all these contributions. So if you think lots of social science problems do not have this structure. So if I this is like, occasionally I get, this actually happened this week. I got an email from someone, I don't know who it was like, I've got this cool thing I've discovered about the relationship between DNA and language structure. I'm like, that sounds neat. And then like, it's like a long thing. And I'm like, it could be cool, but like, I can't read this. Like, I don't have enough time to read all this stuff, but it could be a great idea. And so one of the beauties of Netflix here is that they don't have to read all these things. They can find these best ideas really quickly because they're working with a situation where solutions are easier to check than they are to generate. So Netflix doesn't know the best way to generate a solution, but if they see it's very easy for them to check a solution once someone submits it. And let me just illustrate the power of this. During the Netflix prize competition, this blog post went up. And I showed this in particular because I want to show you some about the context of this blog. Okay? And here's the main idea from this blog post. And I'm just going to read this for 1 second. So in other words, if we take a rank 40 singular value decomposition of the 8.5 billion matrix, we have the best least error approximation we can within the generalizable limits of the user movie rating model, et cetera, i.e. the SVD has found our best generalization for us. Pretty neat, eh? Only problem is we don't have 8.5 billion entries. We have 100 million entries and 8.4 billion empty cells. OK, there's another problem too, which is that computing the SVD of a ginormous matrix is, well, no fun unless you're into that sort of thing. And then it goes on and on and on, and then it ends. So yeah, you mathy guys are rolling your eyes right now as it dawns on you how short the path was. OK, so this was posted by, it actually was an anonymous, someone who, using the screen name Sifter, posted this. So is this a good idea or is it not a good idea? So some of you actually probably know how the Netflix prize was solved and know whether this is a good idea or not. But it turns out that even though this may look like kind of a strange way of writing up a result, this was a really good idea. This moved him into 4th place in the Netflix competition, which was a huge advance, given that other people had been working on the problem for months. And to me, this is so cool. This is so different than the way social science normally happens. So like the number of ideas out there are really big in social science, and we can't quickly tell which are the good ideas and which are not the good ideas. So like basically of all the ideas, lots of them never get evaluated. And then even when they do get evaluated, they get evaluated in a biased way because it's hard to detach the idea from the creator of the idea. I mean, we try, we have blind review, like, and we want to do that. But like, when this person uploaded his contribution to the Netflix prize, he did not upload his CV. He did not upload the fact that where he worked or what his gender was or what his age was. Like, he just uploaded his predictions for what movies people would like, and then they were able to very quickly and clearly see that this was a good idea. And so I wish that there was more ways that as social scientists we could tap into all of the good ideas that are out there. But right now we don't have the way this was set up somehow, the way that the solutions are easier to check, are so easy to check, that is a necessary feature for being able to be open. If it takes a long time to evaluate each solution, then you can't possibly evaluate all of them. So yeah, so the key is that you want problems where the solutions are very easy to check, and that allows you to really be open to anything in the world. So now I'm going to give you an example from social science and try to argue that this is not just limited to these kind of prediction kind of tasks. So like you may have seen the Netflix prize, and you've probably seen a lot of other prizes like that, where it's like a machine learning, you think like some kind of machine learning solution. So this is, I'm going to talk a little bit about peer-to-patent. So this is a project that was run by the US Patent Office, which is maybe not a place you would look for interesting innovation. But actually they had this really neat system. So here's how it works. So imagine that you're a patent examiner and you get a patent that looks like this. So here's a little piece of a patent. A computer system compromising a processor, basic input-output system, include blah, 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 blah. It's like a bunch of mumbo jumbo. And so then you as a patent examiner have to very quickly figure out whether this is actually new or whether there's prior art. And this is a hard job because as a patent examiner, you don't have very much time. You only get about 20 hours per application. And it's also hard because you can't consult with people outside of the patent office. So normally, because the patents have to be secret, and so the review process is necessarily very constrained to ensure secrecy of the patents. And so this struck Beth Novick, who's a law professor, as a very strange system. And what if you could have some kind of open, like peer review system for patents? That would help you find the prior art easier, and it would potentially take a lot of the burden off of the patent office so that things could go faster. So you get potentially better and faster. So here's the schematic of how peer-to-patent works. So first, a patent applicant has to opt into this open system. And the reason they would do that is the patent office said, we will review all these first. You get to basically jump to the head of the line of the patent queue, which is a very exciting thing because the patent queue is very long. So then it goes online, and a community finds and uploads potential prior art. Then the community goes through a voting process to produce the top 10 pieces of prior art. And then those top 10 pieces of prior art are given to the patent examiner to evaluate in addition to whatever review the patent examiner wants to do. So in this way, this whole peer-to-patent process is completely advisory. Like the patent examiner is totally able to just ignore the whole thing and just do whatever they were doing before. Or if there's something good in this top 10 list, they can take it and use it in their decision. And so here, again, this has a very similar structure to the Netflix prize, which is that once someone out there in the world finds some piece of prior art, like this programmer at IBM found some manual from some Intel device that preceded this patent. And once the patent examiner sees that, it's very easy to check whether this is yes prior art or no prior art. And so I think there are potentially more problems than we might realize. There are more problems than just these like machine learning prediction problems that might have this easier to check property. And then those then might be amenable to more open calls where we potentially elicit solutions from a large number of people, even without having to know which of those people are experts or not. So again, some very simple claims summarizing what I've said. Open calls can produce results better than experts, and I put experts in quotes here because I think that like the person who wrote that blog post, even if he is not a professor at Stanford, he is an expert in that he had this great idea that the people at Netflix did not have. I will also now say that at that time, he is not a professor anywhere. He's a software developer. At the time he was doing that, he was backpacking around New Zealand. And I think there's like lots of that stuff. There's lots of great ideas out there if we could somehow build systems that allow us to take advantage of them. And then particularly, we can access insights from people that currently aren't considered experts that actually have a lot to contribute. Yep?
So you introduced the peer-to-patent example as a social science example. What was the social scientific question?
It's not really social science. It's closer to social science. I would say that you could imagine using something like peer-to-patent in history or in searching through like archives. So a lot of times you would want to find like, what's the first, is there a mention of certain thing happening in a certain time period, potentially in settings. If all the relevant documents are in the same place, you could potentially look through the archive yourself. But imagine like distributed kind of archive setting, you could think of something like that. So you're right, it's not really social science in the sense like the Manifesto Project was. But it's closer to social science. But I think you've touched on an interesting point, which is that I don't think there are any, I mean, if you know of any, please tell me. I don't think there are examples of social scientists doing open calls. Yeah.
I'm not sure whether this counts as an open call or as distributed data collection with the recent psychology of data replication.
Yes.
Does that count here, or is that distributed data collection?
I would say it's distributed data collection.
Okay.
And that's actually a good one that I haven't talked about here. But the reason why I don't think it's an open contest is because it's not about a solution to some prize that, or some like criteria that you've specified, and you say, anyone give me something that specifies that criteria. It's more like collect this kind of data and contribute it to a bigger project. So that transitions into the distributed data collection. So I want to talk briefly about Ebird, which is a super cool project about ornithology. So basically what happens is there's a lot of people who like to go and watch birds. And it used to be the case that they would write, they like kept these notebooks and like they were all just sitting in people's closets rotting. And these ornithologists at Cornell said, why don't we just take all these observations that people are making and even writing down on paper and aggregate them into this one giant database of birds. So it tries to take advantage of the work. I put work in quotes because these people actually enjoy going out and watching birds and taking notes about it, but the observations that are already happening. And so there they have about now 200,000 participants have contributed about 250 million observations. This is a case where, again, a small number of people contribute most of the observations, and those people also are higher skill, as best they can tell. So it's hard to actually, they have ways of trying to estimate people's skill as a birder from the data that they have. And based on those estimates, they think the people that contribute the most are also the highest skill, which kind of seems not implausible. But it's actually a little bit hard to do. They have some papers about that. So but the problem is that the data from Ebird is really complex to work with. So, right, identifying birds is hard. And so it's not clear the quality of the data you're getting. So they have ways around this. They have very elaborate and built up over time input filter system. So like if I go on Ebird and report seeing a snowy egret here in Palo Alto today, they're going to flag that and say that's not possible. And then all my reports go to an expert volunteer like coordinator from this area who would then review them and then correspond with me to get additional information to verify what I've done. So they have a lot of automatic screening that goes to these experts. So that gets rid of like pure crazy stuff. But there's still, who knows. Then another even potentially bigger problem is that most of the observations happen where people are, which is not necessarily where birds are. So if you look in Ebird, most birds seem to be near roads. And like, we have a good idea that there are birds not near roads. And this is one of the challenges of getting work that people are doing anyway, is that work is not necessarily the work that you want. And then finally, as we talked about, there's heterogeneity and observer skill. And there's heterogeneity in the protocols that they use to do the observation. So it turns out that there's different ways that you can do birding. So you can like stand in one place and look around, or you can walk, or you can like walk in a certain way. You can imagine like if you want to count the number of birds in a square acre, like there's different procedures, and sometimes people don't follow the procedures that like an ornithologist would follow. Okay. But despite these problems, Ebird has been used in more than 200 papers. So I think when people first hear about Ebird, their first thought is like, oh my God, that data sounds totally crazy. And like that, so the question is this data perfect? No, absolutely not. Is this data better than other available data for certain questions? Yes, and that is evidenced by these 200 papers. So to give an example, a lot of these papers are about how climate change has caused change in migratory arrival times for birds. And so there you can imagine that like just because you're observing near roads, doesn't really matter. You just need to know when the arrival time of the birds is. So having this distributed group of people participating helps you answer that question. So now I want to talk about another project that's actually published in Chi, presented at Chi, that I think is like a really cool project and like really improves on some of the problems that you could see with Ebird, or challenges with Ebird. So this came out of this idea, like there was this project called Build Rome in a Day, where they like took a bunch of photos that people had on Flickr and then tried to like create a 3D reconstruction of Rome, but really just certain, but they really only had certain pictures of certain big touristy sites. And so even those, they had only pictures from very similar angles. So it's a little bit like Ebird in the sense that you're getting these people's pictures, but they're really not giving you the pictures that you want. They're giving you the pictures that they want to give you. And so what if you could somehow come up with a system that would induce people to collect the data that you thought was more important? And so that's what I think PhotoCity did. So they had two different campuses, University of Washington and Cornell, and then they tried to induce people to upload photos so that they could do a reconstruction of the campus. And so they had this complicated game mechanics to do that. And then they had about 100,000 photos submitted by about 45 people, and they get these kind of reconstructions. So but what I want to point out is the really beautiful things about PhotoCity, which are, I think, especially apparent when you compare it to Ebird. So first, the data collection, because it's all done with cameras, is standardized. So none of this like, oh, is this person an expert birder or not an expert birder? Like, camera is a camera. And this, I think, it looks good for the future because as more and more of these observations, this distributed data collection can be done by tools rather than people, that can deal with some of this variation in observer skill. The verification of these things is automatic because what would happen, so in Ebird, you upload that you see a snowy egret, it goes to some expert, they have to check it, and then imagine that I uploaded something else, like I saw a condor. I don't know, I think you can see a condor here. I don't know, but like it's possible, and so it'd be hard to verify that. But so in PhotoCity, the verification is automatic because it looks to the extent to which your photo upload overlaps with some existing photo. So it's like a redundant, built-in sort of redundancy checking, and it won't accept photos that don't overlap. So anything that's in there, you know, overlaps, and then eventually all that overlap goes back to a few seed photos that they uploaded. So the verification is built in, and then also they have this really clever scoring system which gives you more points for the more pixels you add to the reconstruction. And so what they do is they essentially teach the participants to upload more valuable data through this scoring system. And so in the paper, they have these great quotes from the players saying like, oh, I figured out that if I go on a cloudy day, I should go to these kind of buildings, and on a sunny day, I should go to these other kind of buildings. And like, I walk with my camera like this so I can take lots of different pictures at the same time. Like, they really got much, much, much better at collecting the kind of data that the researchers wanted. So I think what PhotoCity really shows is that these things about sampling and data quality are not necessarily insurmountable problems, especially when we use technology more. So I want to tell you about another project from social sciences, which is called the Malawi Journal Project. So this was part of there was something called the Malawi Diffusion and Ideation Change Project. So Malawi is a country in Southern Africa. They have a reasonably severe HIV problem. And so this project was set up to understand how the population thinks about HIV and how they can reduce the spread of HIV over time. So it was a large, like they did surveys, they did collecting health records and things like that. What they also did is they had 22 journalists write down all of the, these are residents of the area, write down all the conversations they heard people having about HIV. And so they've been doing this for a very long time, and now they have this huge number of pages of text of all these conversations that people are having in a natural setting about AIDS. And so what they found, which is really neat, is that these citizen journalists were able to access much different information than the researchers were able to access through these standard survey techniques. And that then any sort of outside Westerner was able to do. So like at the beginning of this project, there was this idea that like AIDS was like an invisible epidemic and people didn't talk about it. That was the sort of logic of people coming out of the World Health Organization and UNAIDS. And this project showed very, very clearly that that was not the case. There's tons of people talking about AIDS all the time. They're just not doing it around people coming in from the World Health Organization. And so there's a couple of other things I like. Another thing that this project showed that was really interesting was like the way that, so condom use is a good way to prevent the spread of HIV, and there were public health campaigns about condom use. And one of the things that this showed is that the way that people talked about condom use with their friends was very different than the way that condom use was framed in the public health messages. So that helps them also understand maybe why some of their outreach techniques are not being very effective. So coming to the claims about the distributed data collection. So it's possible for real research. Sampling and data quality concerns are not insurmountable. And then sometimes it can produce different and not just cheaper data. Like that Malawi Journal Project data, there's no way that Susan Watkins, who is she's a professor at Penn, there's no way that she could have gotten that data. Like the only way to get that data was through this kind of distributed setting. It's not just about saving money, it's also about getting access to different kinds of things. Okay, so I have 1 minute, one more minute? Okay, so I have 5 design principles that I think maybe to try to generalize from these things. But I only have 1 minute, so I'm not going to really be able to spell them out. So first, obviously, you really want to motivate your participants. How you do that, it's not clear. 2, you want to be really accepting of heterogeneity. So I think a lot of times we want to like screen out people who we think aren't going to be good enough or something. And I think the heterogeneity is good. In open calls, it helps us find novel ideas. And in these other systems, it helps create redundancy that allows for verification. So I think a lot of people don't like heterogeneity. I think heterogeneity is good for these. You want to focus people's attention. So one of the things I loved about Photo City is that it had this system that basically induced people to do the more valuable scientific thing. And I think one idea is you just throw it open to everyone, but then you end up wasting a lot of effort. So if you can have some way to channel all this effort into the most meaningful things, that's great. I think you also want to enable surprise. One of my favorite things about Galaxy Zoo is that in addition to labeling the galaxies, which was a task that Galaxy Zoo was created for, the Galaxy Zoo community also found this new kind of galaxy, the green peas. And there's like this long discussion in the forum about these. And then a professional astronomer got involved and helped them. They wrote a paper about that. Then there have been more subsequent papers. Then just recently there was a paper in Nature about these green pea galaxies that were discovered by these people in Galaxy Zoo. Then they offered, this paper in Nature was saying that these galaxies are a potential explanation for some kind of puzzle about ionization in the universe or something. I'm not an astronomer, I don't totally understand it. But the thing that's cool is that it was something that was not intended for the system. Like, if you have a bunch of people thinking about something and working on it, don't prevent them from doing other things that are cool too. And the last principle is be ethical. And this is like always a true thing to say, but I think in this space, the ethical standards are still not totally clear. And sometimes people haven't thought as much about them when they start to do their work. So I would just say like, this is something you want to think about at the beginning, and you want to try to do your best to be aware of it. And so I hope that we can sort of do more cool stuff all together. Thank you.
Yep.
The question in the case of text mining, there's a lot of progress right now in semantic searching, and Google News, semantic search, and all these things. So some of the things that you can do with lots of people doing human computation, you could start generating some type of like, at least baseline with like a semantic algorithm. So where I'm going is like, you're defining data in different levels, right? Yeah, you got good data, better data than others, so you can get better data than nothing with something that will do it in seconds rather than in hours. Should we like use mixed methods between like semantic search and human computation and
Sure. So I think
type of machine learning?
Yeah, no, I think that stuff is all very exciting. So I think that in general, we don't want to waste people's time. And so if the task can be done by a computer, it should be done by a computer. But I think for the foreseeable future, some of the tasks in the human computation space, at least some of the tasks that social scientists will want to do are not, the machine learning techniques are not yet totally available. And then I think for open calls, and it's great if someone has a machine learning technique to do it, great, and someone might have a different technique to do it, and that's great. And like that's one of the beauties of those kind of things is that people can approach them in different ways. And then with distributed data collection, I think, yeah, that one, it's got to be people doing stuff to get the data into the system, which can then be analyzed by these other methods. Yep.
Comment, but I was just going to say that you could avoid a lot of the issues that it seemed like you were trying to avoid if you try to measure things that are true by definition. And what I mean by that is a lot of times in research you're trying to find out what someone thinks, for example.
Yep.
And if it's, if you're measuring personality and it's what they think of themselves, then their self-report is going to be true by definition.
Mm-hmm.
So something that could relate to this would be like if you were actually trying to measure how birds, the distance that birds are to people changes over time. That would be more true by definition. You wouldn't have to worry about, is this a representative sample? And so you wouldn't have to worry about, like, are these people good at measuring galaxies or something, if what you're actually trying to ask them is something that could be true by definition.
Yeah, I like that. I would have to think more about that. But so in general, I like the idea that there are some tasks that are easier than others for this kind of approach. And I think you're right that things that are sort of by definition true should be easier. And then I would have to think more about what kind of tasks or what kinds of things fit into that space. Because a lot of the things like you mentioned, like personality, like that, I would think a lot of it. Then I think sampling becomes more of an issue because who you're talking to potentially, it depends what kind of claims you want to make. But my intuition is that if you're dealing with these definitionally true things, then sampling becomes maybe more of an issue. But I'm not sure. I have to think more about it. But it's a good idea. Yep.
As a sociologist, I have to ask do you think there are non-quantifiable and like maybe non-objective things that you could never verify with such a like Netflix type thing? And if so, should we avoid them and just go for the more low-hanging fruit that could scale up?
So yeah, I don't think that everything is like the Netflix prize, and that when you you can sort of have a clear contest and say one thing is better than the other. I do think, though, as sociologists, I do think we could do better at actually having clear competitions and like being, I think that would spur us to do better things. Like we're sort of like, here's one way to think about this problem, here's another, here's another, here's another, and then like, are we really making progress? I don't know, that's, yeah, so like this is kind of how they do it in some machine learning things where they have like a core data set, everyone tries to do the same task on the same data set, they see which things work the best, and then they do it again, and they do it again and again and again. And over time, they get a sense of like what's actually working and what's not working. And so then when a new thing happens, it's clear whether that new thing is good or not, which is like, to me, so cool. And it doesn't matter who you are or where you are. It's like, if this is the task and this thing does the task well. And then we can figure out why, and we can figure out how to make it better.
One wrinkle on that, it doesn't have to be automatically, as long as it's much faster to sort of evaluate than it is to generate.
Well, it just seems like some things aren't just true or not. Like if you talk to a qualitative persona, this would make sense. So.
Well, wait a minute. So I want to. So like the Malawi Journal Project, that is absolutely qualitative, and they think of that completely as like a distributed ethnography. And so another way to think about the distributed. So I think the Netflix stuff has that property, but like let's take the peer to patent. Like there, I could say I want to find examples of personal correspondence between people that illustrate the theme of. Like, let's say I argue like love, the modern notion that we have of love is a totally new creation. And then I say, well, can anyone show me an old personal letter that has the notion of love that we have today? I mean, that's something you could imagine doing an open call for.
I would also argue that citations are a sort of more ancient version of this, right? If we have different theories about love or something like this, eventually his is going to be better, and he's going to gather a larger mind share.
But I disagree with you. I think citations are not a good. I mean, I think like the lesson that I draw from the music experiment is that that like basically people's attention is very limited, and they focus on things that are already popular, and then those things become more popular, and a lot of good stuff gets lost.
Yeah. Thanks. This is really cool. So the big question this raises for me is about professional status.
Yep.
So as data science sort of rolls into the sciences, you can imagine sort of a range of different sort of jurisdictional defenses. So you spoke a little bit about sociologists being sort of skeptical of the validity of the results, for example. Do you have any sort of observations about how different sciences are sort of responding?
Interesting. I think so. I think. Ornithology, I think, is more accepting because they have a long tradition of this. This goes back a long time in ornithology, like hundreds of years. So to them, it doesn't seem weird. I think part of it is that a lot of the concerns people have, in my mind, are not very specific. They're just like, because it's weird. I mean, like, let's be honest. Like, some of the stuff is like very different than what people are used to, and it's appropriate to be cautious, right, and skeptical. And so I think, like, what I hope is that we move beyond that first just blanket skepticism to more specific questions like, oh, well, is there a correlation between amount of data contributed and skill? And then we can like make progress in a kind of a normal way. And I do think the thing about professionalization and status is a concern. And I wish it wasn't. But like, actually, so it's interesting. So when I talked to a graduate student about this, about the open calls, and she was like, so what does the researcher do then? Like, you're not really solving the problem. And I'm like, no, that's like that's like a huge contribution to like pose the problem correctly and motivate a whole community of people to work on it. Like that's, I think, what thinking about what research impact is not like about solving specific problems, but changing the way people think and getting people excited about new things. So I think in some ways, like this is just posing the right question and organizing the right kind of system, even if you're not doing the bits and pieces of the work, is an enormous contribution that you can be making to science.
Sorry. You can take questions after we end, but thank you for one more time.